charge density. It is simply the magnitude of charge per unit surface area of the species. Higher is the charge density of a species, more unstable it becomes. Here it must be made clear that it is the magnitude of charge and not with the sign. The stable species is with a zero charge density. A high charge density species can replace a low charge density species from its compound. Hydration. A more general term is solvation. When the solvent is specifically water, it is termed as hydration. If any species is added to water, it will have some interaction with water molecules. These interactions may lead to breaking of water-water bonds. The bonds between the constituent particles of the species and formation of bonds between water and the species which has been added. Water has hydrogen bonds holding together the molecules of water. These are the strong intermolecular forces. For them to break, the bonds of the species and water must be strong enough. Generally, two interactions have the capacity to overcome the hydrogen bonds between the water molecules. The first one, the species is capable of forming hydrogen bonds with water, so that the energy released when the species forms hydrogen bonds with water is able to overcome the attractive force between water molecules and break them. The second, the species breaks apart in water to form ions. These ions interact with the dipoles of water molecule to give ion-dipole interaction. These interactions are quite strong, quite significant, and are easily able to overcome the attractive forces between water molecules. If a species cannot form hydrogen bonds with water, and it does not even dissociate to form ions, then it can be safely said that the species does not have any significant solubility in water. If we consider oil on water, then it is generally said that oil does not dissolve in water. But if we look closely, the oil drop actually spreads on the surface of water, signifying that oil actually loves the interaction with water. It is the water which does not allow oil to mix. The weak van der Waals forces between water and oil are enough to break oil-oil bonds, but are not enough to break water-water hydrogen bonds. When a species forms strong enough bonds with water, which could be hydrogen bond or ion dipole interaction, water forms a layer surrounding the species. This surrounding layer is termed hydration sphere. The hydration sphere could be single layered or multiple layered. In the formation of this sphere, energy is released as the bonds are being formed. This released energy is termed as hydration energy. Hydration. The attachment of water molecules to a species either through the formation of hydrogen bond or ion dipole interaction without breaking of water molecules is termed as hydration. Hydration sphere. The single or multiple layers of water molecules formed around a species is termed hydration sphere. Hydration energy. The energy change when a species is hydrated is termed as hydration energy. This energy compensates for the lattice energy of the solid and plays a major role in solubility of substances in water. Hydration of ions is completely dependent on their charge density. A higher charge density ion will form a stronger and larger hydration sphere and release more hydration energy. A typical example is of lithium ion and cesium ion. Lithium ion is extremely small cation having a very high charge density. Because of this, it forms a huge multi-layer hydration sphere and releases exceptionally high hydration energy amongst alkali metals. It makes lithium ion the most stable alkali metal ion in solution, and lithium becomes the strongest reducing agent in the aqueous medium. The hydration sphere of lithium plus moves along with it, making it the largest alkali metal ion in the aqueous medium. This makes the ionic conductance or the ionic mobility of lithium ion the minimum amongst alkali metals. Cesium plus is as such the largest ion, but its hydration sphere is the smallest. Its effective size in the solution is the smallest amongst alkali metal, which makes it the best ionic conductor with the highest mobility in solution. Hydrolysis. It is the reaction involving the breaking of a bond in water to form H plus and OH minus by a species. In this process, the species consumes H plus or OH minus, or in some cases both. An electron deficient species would consume hydroxide ion, that is OH minus, from water and increase the concentration of H plus in the solution, making it acidic. While an electron rich species will consume hydronium ion, that is H plus, from water, increasing the concentration of OH minus in the solution, making it basic. If a certain ion has a higher charge density, that is comparable to H plus or OH minus in water, then it may consume the oppositely charged ion from water to reduce its charge density. This would lead to hydrolysis by the ion. This is termed as ionic hydrolysis. If the cation has a high charge density, it would cause hydrolysis. The hydrolysis by the cation would consume the hydroxide ion and increase the concentration of H plus. So, cationic hydrolysis makes the solution acidic. If the anion has a high charge density, it would lead to anionic hydrolysis. The hydrolysis by the anion would consume the hydronium ion and increase the concentration of the hydroxide ion. So, anionic hydrolysis makes the solution basic. Hydration is surrounding of a species by water molecules forming a single or multiple layer through hydrogen bonding or ion dipole interaction. Hydrolysis is the reaction involving breaking of bond in water to form H plus and OH minus by a species. In this process, the species consumes H plus or OH minus, or in some cases, both. A compound formed along with water in the reaction of an acid with a base is termed as salt. It is either obtained after the evaporation of the solvent, that is water, or simply precipitates out if it is insoluble. It is an ionic compound and is a strong electrolyte. There are two kinds of acid, strong acid and weak acid. And there are two kinds of bases, strong bases and weak bases. So there are four types of salt. A salt formed by the reaction of strong acid with a strong base, such as sodium chloride. A salt formed by the reaction of a strong acid with a weak base, such as ammonium chloride. A salt formed by the reaction of a strong base with a weak acid, such as sodium acetate. A salt formed by the reaction of weak base with a weak acid, such as ammonium acetate. While discussing the salt hydrolysis, it must be clearly understood that all the derivations are for moderate dilute solution, that is 0.1 molar. A salt capable of forming 0.1 molar solution is considered soluble. Between 0.01 to 0.1 as slightly soluble, and below 0.01 as sparingly soluble. Let us consider formation of sodium chloride solution. Sodium chloride is soluble enough to form 0.1 molar solution. It dissociates in water to form sodium and chloride ions. The hydration energy due to the ion dipole interaction is able to compensate for the lattice energy and the energy required to break hydrogen bonds in water. The small deficiency is overcome by the increase in randomness, that is, the entropy on formation of a solution. The process is slightly endothermic but does take place. Sodium and chloride ion get surrounded by water molecule which form the hydration sphere. Na plus is a large cation which has a much lower charge density compared to hydronium ion. Although it gets sufficiently hydrated to be soluble in water, it has no tendency at all to pull hydroxide from water and show hydrolysis. In the same manner, chloride ion, Cl- has a large surface area and low charge density, much lower than the hydroxide ion. It does not have any tendency to accept hydronium ion and hydrolyze. The hydration energy again is enough to overcome the lattice energy, but hydrolysis requires much stronger interaction and does not take place. In this salt, the cation and anion both have low charge density and are stable in solution. So the simple statement is the salt formed by the reaction of a strong acid and a strong base does not hydrolyze and the solution is neutral. Now to consider the next example. Salt of a strong acid and a weak base. Let's consider the formation of ammonium chloride solution. Similar to sodium chloride, ammonium chloride easily dissolves in water to give 0.1 molar or even more concentrated solution. The ammonium and chloride ion get hydrated. In this salt, the anion, that is the chloride, is the conjugate of a strong acid, that is hydrochloric acid. It has a low charge density and is very stable. The cation is a conjugate of a weak base, ammonium hydroxide. Ammonium ion is surrounded by water molecules. The oxygen in water is not as good electron donor as nitrogen in ammonia. So ammonia has a much higher capacity to hold on to the H plus compared to water. Still, the concentration of water is much higher in comparison to ammonia, and this allows some of the ammonium ions to lose H plus to water and increase the concentration of hydronium ion. So we say ammonium ion is not much stable and hydrolyzes. In this reaction, cation has caused the hydrolysis, so we consider the salt to be showing cationic hydrolysis. It increases the concentration of hydronium ion, making the solution slightly acidic. Ammonium aqueous interacts with liquid water to give ammonia aqueous and hydronium ion aqueous. This is cationic hydrolysis. This equation may be written as ammonium ion reacting with water to give ammonium hydroxide aqueous and H plus aqueous. In this reaction, on the left hand side of the reactant, one of the reactant is water. It is present in excess and is the solvent. Although there are two reactants, this reaction will have only one term in the denominator of equilibrium expression. Since water being the excess amount and the solvent, its concentration is a constant. This is simply considered a single reactant reaction, and again, the degree of dissociation can be used here. The slight change that we do for this particular reaction is that call it the degree of hydrolysis and denote it by H instead of alpha. As per the previous reaction that we have seen, ammonium ion interacts with water molecule and hydrolyzes to form ammonium hydroxide and H+. Per mole of ammonium ion, 1 mole of ammonium hydroxide and 1 mole of H+ will be produced. So, from H moles of ammonium undergoing hydrolysis, H moles of ammonium hydroxide and H moles of H+ will be formed. As is visible, H+ is formed and has a slight high concentration, making the solution acidic. To get the final concentration in the solution, we multiply the entire equation by the concentration of the salt C. The equilibrium constant for this reaction is termed hydrolysis constant or Kh. The Kh is the product of the concentration of ammonium hydroxide and H+ divided by the concentration of ammonium ion, that is the salt. Neglecting the degree of hydrolysis in comparison to 1 in the denominator, we get the hydrolysis constant equal to the concentration of salt multiplied by the square of degree of hydrolysis. Now, the hydrolysis constant H would be equal to the under root of the hydrolysis constant divided by the concentration of salt. In the same manner, the H+ concentration, which is concentration of salt multiplied by the hydrolysis constant, will be equal to under root of hydrolysis constant multiplied by the concentration. Now this equation can be obtained by addition of two equations that we have done earlier, namely the dissociation of water and dissociation of ammonium hydroxide. Writing the two equations, the first one is autoionization of water, having the equilibrium constant as the ionic product of water Kw, and the second equation is the dissociation of ammonium hydroxide. If the second equation is subtracted from the first, the equation obtained is the same that we have written for the hydrolysis of ammonium ion. If the two equations are added, the equilibrium constant of the resultant equation is the product of the equilibrium constant of the two equations. If one is subtracted from the other, the equilibrium constant of the resultant equation is the equilibrium constant of the other divided by 1. The hydrolysis equation is obtained by subtracting the dissociation of ammonium ion from dissociation of water. Hence, using this concept, the hydrolysis constant is ionic product of water divided by the dissociation constant of ammonium hydroxide. Using this expression, the degree of hydrolysis is the square root of ionic product of water divided by the product of dissociation constant of ammonium hydroxide and concentration of salt. The hydronium ion concentration is the concentration of salt multiplied by degree of hydrolysis. It is the product of the hydrolysis constant and concentration divided by the dissociation constant of the base. Taking the log and then the negative log of the equation gives the pH of the salt solution. The pH turns out to be half of pKw minus log C minus pKb. This way, we can find the pH of a solution of a salt of weak base with a strong acid. A question: calculate the pH of a 0.1 molar solution of ammonium chloride at 298 Kelvin. Take the Kb as 10 raised to the power minus 5. Now to consider the next example: salt of a weak acid and a strong base. Let's consider formation of sodium acetate solution. Similar to sodium chloride and ammonium chloride, sodium acetate easily dissolves in water to give 0.1 molar or more concentrated solution. The sodium and acetate ion get hydrated. In this salt, the cation, that is sodium ion, is the conjugate of a strong base, that is sodium hydroxide. It has a low charge density and is very stable. The anion is conjugate of a weak acid, acetic acid. Acetate ion as well as sodium ion are surrounded by water molecules. The oxygen in the acetate ion has a high charge density. This has a tendency to attract hydrogen ion from water. Although the charge density of hydroxide ion formed from water after losing the hydrogen ion is more than the acetate ion, still it is somewhat comparable and takes place to a small extent. This increases the concentration of hydroxide ion in the solution and makes the solution slightly basic. Here, the anion is responsible for hydrolysis. It is termed anionic hydrolysis. In this reaction, on the left hand side, one of the reactant is water. It is present in excess and is the solvent. Hence, although there are two reactants, this reaction will have only one term in the denominator of the equilibrium expression. This is considered a single reactant reaction and degree of dissociation can be used. The slight change we do here is call it degree of hydrolysis and denote it by H instead of alpha. As per the previous reactions we have seen, acetate ion interacts with water molecule and hydrolyzes to form acetic acid and OH minus. Per mole of acetate ion, 1 mole of acetic acid and 1 mole of OH minus will be produced. So, from H moles of acetate ion undergoing hydrolysis, H moles of acetic acid and H moles of OH minus will be formed. As is visible, OH minus is formed and has a slight high concentration, making it the solution basic. To get the final concentration in the solution, we multiply the entire equation by the concentration of the salt, C. The equilibrium constant for this reaction is termed hydrolysis constant. Kh is the product of the concentration of acetic acid and OH minus divided by the concentration of acetate ion, that is the salt. Neglecting the degree of hydrolysis, that is H, in comparison to 1 in the denominator, we get the hydrolysis constant equal to the concentration of the salt multiplied by the square of degree of hydrolysis H. Again, the degree of hydrolysis is equal to the square root of hydrolysis constant divided by the concentration of the salt. In the same manner, the concentration of hydroxide is equal to the concentration of the salt multiplied by the degree of hydrolysis, that is equal to the under root of the hydrolysis constant multiplied by the concentration of the salt. This equation can be obtained by the addition of two equations that we have done earlier, namely the dissociation of water and dissociation of acetic acid. Writing the two equations, the first one is autoionization of water having the equilibrium constant as the ionic product of water Kw. And the second equation is the dissociation of acetic acid. If the second equation is subtracted from the first, the equation obtained is the same that we have written for the hydrolysis of the acetate ion. If the two equations are added, the equilibrium constant of the resultant equation is the product of the equilibrium constant of the two equations. If one is subtracted from the other, the equilibrium constant of the resultant equation is the equilibrium constant of the other divided by 1. The hydrolysis equation is obtained by subtracting the dissociation of acetic acid from the dissociation of water. Hence, using this concept, the hydrolysis constant is the ionic product of water divided by the dissociation constant of acetic acid. Using this expression, the degree of hydrolysis is the square root of ionic product of water divided by the product of dissociation constant of acetic acid and concentration of salt. The hydroxide ion concentration is the concentration of salt multiplied by the degree of hydrolysis. It is the product of hydrolysis constant and concentration divided by the dissociation constant of the acid. Taking the log and then the negative log of the equation gives the pOH of the salt solution. Subtracting the pOH from pKw, we get pH. pH is pKw minus pOH, that is equal to pKw minus half of pKw minus log C minus pKa. Finally, the pH is half of pKw plus log C plus pKa. This way, we can find the pH of a solution of a salt of weak acid with a strong base.